Today we start our first of two sections on polar coordinates. And polar coordinates are written in this form, r theta, where r is the radius and theta is the angle measure. And so this is actually a circular coordinate system rather than a rectangular coordinate system. So r is going to tell us how far from the center, how far from the origin our point is. And theta is going to tell us how many degrees or how many radians, normally radians in calculus, we have to move along the not so unit circle. All right. So we've got some polar coordinate paper here. And we're going to have a radius of 1, but the first thing I've got to find is I've got to find my theta. So I got to work my way around and find 5 pi over 4. So I'm here. Let me see, there's pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4. Here's 5 pi over 4. But I only want a radius of 1, so my angle is this angle right here. I've got to come out to a radius of 1. And so that is my point right there. And I'm going to erase the rest of this because if I'm just plotting a point, I don't need all the rest of this stuff. I just need to be at the appropriate angle measure and at the appropriate radius. All right, 3 pi. Well, let's see, I'm here, and here's 1 pi, here's 2 pi, and I'm back over here. Here's 3 pi over here. And in that direction, I have to move out 2 units, so that'd be right to here. And so when I plot this point, that would be my point. And here, 3 pi over 4. 1, 2, 3 pi over 4 is right here. So I'd like to go out -3. Well, anything I move out in that direction is actually a positive movement, which would mean what I'd actually have to do is I'd actually have to face in this direction from the origin here, but I got to back up 3 units. That would be facing in the 3 pi over 4 direction, but having moved backwards 3 units. So that's kind of a summary of polar coordinates. Now, if we want to convert from polar coordinates to rectangular coordinates, we do that using parametric equations that we discussed in the beginning of Chapter 10, where to find the x value in rectangular coordinates, we take the radius times the cosine of the theta that we are given, and the y value is the radius times the sine of theta that we are given. So write the parametric form of r equals cosine 2 theta, then find the Cartesian or the rectangular coordinates when x is pi over 4, or theta is pi over 4. Well, x equals r cosine 2 theta times the cosine of theta, and y is equal to r, which is the cosine of 2 theta, times the sine of theta. All right. And theta is pi over 4, so I need the x value. I'm going to take the cosine of 2 of these pi over 4s, which is pi over 2. Multiply that by the cosine of pi over 4. And the cosine of pi over 2 is 0 times square root of 2 over 2. And actually, I'm going to run into the exact same thing here. I will be having the cosine of pi over 2 times the sine of pi over 4. But since the cosine of pi over 2 is 0, I'm going to get 0. So the rectangular coordinates are 0, 0, or the order. Now, we're going to use our calculators. You're going to grab your calculator, and I'm going to talk you through how to graph this. Now, the first thing you're going to have to do is you are going to have to change your mode. So go to the mode button. And you're going to have to arrow down to function, parametric, and go to the third selection, which is polar. And once I have pressed enter and selected polar, I now go to y equals, and I put in 1 plus sine theta. And you'll notice that the x key, which when we were doing parametrics gave us the variable t, now that we're in polar mode, the x key will give us the variable theta. Now I've also got to set my window. And I think for all of these to say I want theta to have a minimum value of 0 and a maximum value of 2 pi is a good idea. And you can set the theta step, much like we set the t step the other day. Set that at 0.1, I think, is a good idea. It's a smooth graph. And as I look at these graphs, I think for each one of them, to have an x min of -3 and an x max of 3 and going by ones, I think is appropriate. We seem to go -3 up to 3. Same thing for the y's. I think we go from 3 to -3. I should say from -3 to 3. And to go by ones. Now, if I graph this first one correctly, I think what I get is something that looks sort of like this. Well, let's see now. I better be a little bit more accurate. Let's see, I think we go something like that. Looks like an upside down heart. I think the official name for a function that looks like that is a cardioid. Now, if I go to my y equals, get rid of that first one. Let's do the second one. Cosine 2 theta. Cosine 2 theta. And I'm going to graph that. When I graph that, I got to look at that again. I got to see exactly that happened. Now, one thing I'm going to encourage you to do, and this is difficult to tell you without showing you the calculator, but it does say R1 when you're putting this in, and you're going to say equals cosine 2 theta. But what I'd like you to do is I would like you to use your left arrow, and I'd like you to arrow over here to the left of R1. I want you to arrow over to this symbol right here. And I want you to change that symbol by pressing enter. and I want you to change the kind of a line. I want you to replace this with the symbol that looks like this. Because what that's going to do is it's going to show you how this figure is being drawn. So if I graph this thing again, I think that this looks like this. Let's see, it's in blue. I'll do mine in blue. See, I think it goes here, here, back to the origin, back to here, down to here, up to here, down to here, and then finishes right back where it started. Now, that's not the best little four-leaf clover, but you get the gist of it. You go out to 1 and -1, up to 1, down to -1. And that's what you get. And you'll notice that if you used the type of line that draws like this, that it shows you where it's been, where it's going, and that's going to be important. As we do the third one here, y equals, let's clear this cosine 2 theta out and put in sine 3 theta. And when I press graph, if you've got the little bubble with a tail on it, like we've got right here, I think you notice that it traces over itself 2 times. It comes out here and it does the first quadrant. Down here does that guy. Up here does that guy. And then it goes over itself again. Now what that tells you, which is going to become important, is that to draw this entire figure, we don't need to go from 0 to 2 pi for theta. That we can get that entire figure done and drawn just by going from 0 to pi. It's going to be important as time goes on. So anytime you draw a graph in polar coordinates, make sure that you are using this kind of a line anytime you draw something in polar, so that you know where it is and how many times it traces over itself. Okay? Not real important right now, but it will be. So make sure your calculator is set that way. All right. Now, third slide. Final slide. Find the slope of the parametric equation, of the polar equation. And we're going to treat it like it's a parametric with theta as the parameter. So if we want to find the slope, which we generally write as dy dx, we can find the derivative of y with respect to theta, kind of like we did dy dt over dx dt. We're now going to do dy d theta over dx d theta. All right, so that's going to help us find the slope of the polar equation. And that is our next task right here. Find the slope of the tangent when theta is pi over 3. Well, the x is r cosine theta. And y is r times sine theta. So if I want to find the slope, I have to start with dy d theta, and I've got to find the derivative of this guy with respect to theta. It's going to involve the product rule. Dy d theta equals, let's see, first 1 plus sine theta times derivative of the second, which is cosine theta, plus the second, which is sine theta, times derivative of the first, which is cosine theta, over dx d theta. Which is also going to involve a product rule. A first times derivative of the second plus the second times derivative of the first. And then what we're going to need to do, now that we have found the derivative, is just replace theta with pi over 3. Now, we know what the sine and cosine of pi over 3 are. We know we'd have 1 plus square root of 3 over 2 times cosine is 1/2 plus the sine, square root of 3 over 2 times the cosine, which is 1/2, and divided by, well, still 1 plus square root of 3 over 2 times the opposite of the sine, negative square root of 3 over 2, plus the cosine, 1/2, times the cosine, 1/2. And if we do all of this successfully, I think we get a -1. So double check, make sure that that's indeed what you get. Now, final task, pretty involved task. Find a point where the tangent is horizontal. Find a point and one point where the tangent is vertical. Well, if I want a horizontal tangent, that means the slope is 0. And anytime the slope is 0, that means that the top of the fraction, in this case dy d theta, has got to be equal to 0. So if I take this dy d theta and maybe multiply it out and simplify it a bit, if I multiply this out, I think I would get cosine of theta plus sine theta cosine theta plus sine theta cosine theta and I want that to equal 0 because that's going to be a horizontal tangent. And actually, if I were to combine like terms, I think that what I would have is 2 of those sine theta cosine thetas. So that's what I want to equal 0. So I think that what I will do is factor out a cosine. Cosine of theta times 1 plus 2 sine theta. And I would like that to equal 0. Well, all right. What are my values of theta that are going to give me 0? Now, when is the cosine 0? Well, that happens at pi over 2. That happens at 3 pi over 2. That happens, now let's see, what makes this 0? When is the sine -1/2? So I think of my unit circle, and sine is -1/2. 7 pi over 6, 11 pi over 6, but you know what? This only asks for a single point where the tangent is horizontal. And actually, I even know what this thing, let's see. I even know what this thing looks like. We graphed that earlier. We have this cardioid. Something like that. And yeah, it seems as if up here at pi over 2 that we would have a horizontal tangent. And so I am going to find the point when theta is pi over 2. If I put my theta is pi over 2 in for x and in for y, let's see what we get. I put that in for x, 1 plus 1 times nothing is nothing. I get an x value of 0 and a y value of 1 plus theta is pi over 2. 1 plus 1 times 1. It appears as if I would have a horizontal tangent right up here at the point 0, 2, and that certainly isn't very difficult to understand. Okay, cool. So that's one point, and I'm happy with that. We'll talk about other things that may have happened shortly. Let's talk about verticals now. Now, for a vertical tangent, wouldn't that mean that the bottom of our slope equation, our slope fraction, would have to be 0? Now, if I multiply that out successfully, I'm going to get a negative sign minus sine squared theta plus cosine squared theta. And I want that to equal 0. And I'm almost excited because I'm almost thinking, oh, hey, there's a trig identity, but one of them's negative and one of them's positive. So I'm going to have some significant work to do here. I'm going to call this negative sine theta minus sine squared theta plus 1 minus sine squared theta. There's use of that trig identity. I want that to equal 0. Now, if I kind of combine like terms and rearrange this just a bit, I know I got a 1. I know I've got a minus sine theta. And I know I've got minus 2 sine squared theta. And that is equal to 0. Well, now, like we did for the horizontal tangent, I'm going to factor. And I think this is going to come out to be 1 minus 2 sine theta times 1 minus sine theta. And that's what I want to equal 0. Well, what are my values of theta that make that happen? I need the sine of theta to equal a half, and then this factor is going to be 0. And theta is a half at 5 pi over 6. And at, oh yeah, just plain old pi over 6. Yeah, okay. And when is theta equal to 1? I'm sorry, this is supposed to be a plus, isn't it? I goofed up there. when is theta, when is sine equal to -1, and that is 3 pi over 2. Now, you might notice something here. Didn't 3 pi over 2 appear as both a horizontal and a vertical? See, 3 pi over 2 is right here. That's called an extraneous answer because your tangent's not horizontal, nor is it vertical there. Yeah, at that point, we've got a corner. We don't have any kind of a tangent there. So that one actually turns out to be trash. I do think that there's a vertical tangent right here at pi over 6. I do think there's a vertical tangent right here at 5 pi over 6. I think there's a horizontal tangent at 7 pi over 6. And I think if we extended that, we'd hit right here, which is the point where theta is 11 pi over 6. So I think these all make sense, but 3 pi over 2 does not make sense. Remember, our task here, though, is we've got to find a point where we've got a vertical tangent. So if I say that theta is equal to pi over 6, and say, okay, I'm going to take theta as pi over 6, and I'm going to put that in again right up here and find out what's the point at pi over 6. And theta is equal to pi over 6. If I put that in for the x and I put that in for the y, you see what you get. I'll tell you what I get. See if we agree. I think we get 1.299 and 0.75. This point right here, pretty believable that it's 1.299 and 0.75. So that is our introduction to polar coordinates, graphs of polar functions, as well as our introduction into finding slopes, tangent lines to these kinds of functions. And your assignment awaits you in Schoology.